All right, welcome to our first video assignment notes. This is for week 1. This will be a reoccurring theme every week that we have content. And this is for week 1, we don't have an assignment for you to watch the video before our first class, but this is the video you need to watch before our second class. So if you're in my Monday, Wednesday classes, that would be the Wednesday class. You need to watch it before then. And if you're in my Tuesday, Thursday class, you need to watch it before the Thursday class. The videos will always be embedded on those class notes page. I'll show you where that is in class the first day if you don't find it on your own. And then what you're going to do, the goal of each of these weeks is that you're going to fill in your notes on your own paper, or you can print this out and write on this if you want. You'll take pictures of your notes and then you'll submit them to the assignment in the Ivy Learn video assignment week 1. We'll have one for every week that we have content. So we're going to go ahead and get started. So, looking at this first topic, this is one that is going to show up on your homework, but is not on any quizzes or exams. We wanted to do some practice with mixed numbers and improper fractions. So a proper fraction, there's a definition right there, has a numerator, which is the top value of a fraction that is smaller than the denominator, which is the number that's on the bottom, such as 8/9. Notice that 8 is smaller in value than 9. A mixed number is formed by combining a whole number and a proper fraction, such as 4 1/2. So this is a mixed number. Notice the whole part and a fractional part. An improper fraction has a numerator greater than the denominator, such as 9/2. So notice the top number has a value greater in value than the bottom number, 2. And that is what it makes it an improper fraction. This actually is 4 1/2 written as an improper fraction, because if you divide 9 by 2, you'll get 4.5, which is 4 1/2. So just to re-diagram kind of what we've talked about, a mixed number has the whole number part, a numerator, and a denominator. So what we want to practice in this section is converting between mixed numbers and improper fractions. So to convert a mixed number to an improper fraction, you'll follow these steps, or you do have the ability to use your calculator. I will be posting a separate resource video on that, so that will be just right underneath this one that is required. You can multiply the whole number part by the fraction's denominator. That's our first step. So we're going to do the whole number part and the denominator multiplied together, so times. Then we'll add that product, 2 times 5, to the numerator. So we're going to add the 1 to that. And that's going to be the top of our improper fraction. So 2 1/5 will be 10, which is 2 times 5, plus 1, which would be 11/5. So let's do another example, just so we make sure we've got that down. So we're going to convert 3 2/5 to an improper fraction. So notice we do 3 times 5, which is 15. We add the numerator to that, so plus 2 would be 17, and we write that over our original denominator, so 17/5. And again, like I said, there's a separate video you can look at about how to use your TI-30XS to work between mixed numbers and improper fractions. There's actually a conversion button. Here are some button symbols to be looking for on that calculator, but I will be posting that as a separate video resource. Okay, so let's look at this one. This is writing a ratio, which is something we're going to learn about in our class, of 2 7/8 to 2 1/8. So when we look at this, when you write a ratio, there's a couple different ways we can write it. We learn about this in our first class session. A to B, and you can write that as A. So if you have anything that is a ratio, we can write it as A to B, A colon B, or A over B. We can also go ahead and divide those and get it as a unit rate of whatever that value comes out to, even if it's a decimal, over 1. But for this part, we're going to be writing it as a stacked fraction here. So we have 2 7/8 to 2 1/8. So this is our A and this is our B. First, make them both improper fractions. So 2 times 8 plus 7 would be 16 plus 7, which is 23 over the original denominator of 8. 2 times 8, which is 16, plus 1, because that's our numerator for our second one, is 17 over 8. Now, recall from previous knowledge of other courses that if you do division with fractions, we actually multiply by the reciprocal. And a nice way to remember how to do that is we leave the top fraction alone. We change the division in the middle to multiplication, and we flip the second fraction to its reciprocal. So we are multiplying the first fraction by the reciprocal of the second fraction. So if we write our two parts, remember A and B, as A over B, then this would be leave 23 over 8, change division right here, because that's what that symbol also represents, to multiplication, and we multiply by the flip or reciprocal of the second fraction, so 8 over 17. What you'll notice here is that we could just multiply across. Our numbers would be bigger than we see here, but because we have multiplication, you can cross reduce. That means if there's something that goes into both of these numbers evenly, we can divide by it. And since they're both 8, we can divide them both by 8. So that makes this 23 times 1 over 1 times 17, which is 23/17. So let's try one together. So first step is I'm going to get both of these into improper form because that's easier to work with the multiplication step that we need to do at the end. So we're going to be doing our A to our B. So this would be 3 times 7 is 21 plus 2 over 7. So that comes out to 23 over 7. 2. This would be 4 times 5 is 20 plus 3 all over 5. That's going to be 23 over 5. Stack it. It's going to be A over B for our ratio, since they told us 3 2/7 to 4 3/5. And we're going to do, remember, leave the first fraction alone as it is. Change our division to multiplication. You can write the X or a dot if you prefer, if you like that better for multiplication. And then flip the second fraction to its reciprocal. Now, we got lucky again here. These are reducing because they're both divisible by 23, and we are multiplying, so that is a appropriate way to reduce the fractions before multiplying. So 1 times 5 is 5, 1 times 7 is 7, so we get 5/7. Okay, so that is, like I said, on the homework, the mixed fractions and improper fractions, but not on any quizzes or exams. So you do need to know that to do a few of your homework questions. Now we're going to be looking at things from this point on that are definitely on homework, quizzes, and exams. So these are all topics that you will also be assessed on. So looking at scientific notation, we're going to be doing some of this in our second class meeting together as well, but because we are short on time in a lot of our class meetings, and these courses are designated, we only meet 3 hours a week, and it's 6 contact hours. We have another 3 hours of content that you kind of are working on your own. So some of that is working in your Newton homework. Some of it is these weekly videos. So you do want to make sure you're taking really good notes on these parts and that you are learning this material for your homework, quizzes, and exams. So scientific notation is a way of writing very large or very small numbers in a more compact format. So to be in scientific notation, and when we say scientific notation, we mean proper scientific notation, a number must be written as a product of two numbers such that a number greater than or equal to 1 and less than 10. What that means is it has to be a single digit 1 to 9, needs to be to the left of your decimal point. So when you're writing in scientific notation, you're going to have a decimal point. We want this to be a single digit 1 to 9. Okay. It's going to then have possibly things after it, other digits, or maybe it doesn't. If it's just a singular digit, it might just be 3 times 10 to the something. But we usually will have some other digits afterwards. And then we'll have times 10, a power of 10, with an integer exponent. That is really important. Integers are numbers that are, first of all, the whole numbers. So 0, 1, 2, 3, all the way up as far as we can go. But also their opposites or their negative counterparts. So it's -1, -2, -3, as far down as we can go. So that's what we mean by an integer exponent. So this part up here needs to be an integer. Okay. Now, here are some examples of proper scientific notation. 6 times 10 to the 4th. Notice that 6 doesn't show its decimal, but if you don't see it there, it is actually directly after that single digit. Okay, so anytime you see just a digit, it's really, you can think of it as that number 0.0. You don't have to write that, but that's kind of where the decimal is. It's right after the 6. Now, this has a single digit 1 through 9 in front of our decimal to the left of it, and it has an integer exponent. 4.2 times 10 to the third, single digit 1 to 9 in front, times a 10 to an integer power. 5.67 times 10 to the negative 3. That has the single digit 1 to 9 in front and an integer exponent. 3.76 times 10 to the negative 8, also single digit 1 through 9 in front of the decimal to the left of it, and an integer exponent. The next examples are not in proper scientific notation. So let's talk about why. So for this one, notice my decimal would be right here. This is 42.0 if we want to think of it as showing its decimal and what's after the decimal. This is not a single digit to the left of the decimal. So that's what's wrong with this first one. This looks like it's okay, 0.7 times 10 to the fourth, but actually it's not, because this needs to be a 1 to a 9, okay? So that's why this one is not in correct, proper scientific notation. It does have the integer exponent, but the number up front is not in correct form. This one looks promising. It's 4.0, or just 4 times 10, but this is a decimal exponent, not an integer exponent, okay? All right, so how do we put something in proper scientific notation? So we're going to move our decimal if needed. If it's already got a singular digit 1 through 9 in front of it, we wouldn't need to move it, so that there is one non-zero number in front of the decimal point to the left. And remember, that means a digit 1 to 9. If the decimal moves to the left, if we move it to the left to make that occur, we'll add the number of places the decimal moved to the exponent. Start at 0 if the value is in standard form. So what they mean by that is if you had 742, we think of that, if we put it in scientific form right now, even though it wouldn't be proper, we think about that as times 10 to the 0. 0 means no movement at all, and also 10 to the 0 is the same thing as 1. You can check that on your calculator. So this is kind of our starting point. Here our decimal is, we would need to move it 2 places to the left to make that proper scientific notation. So if we do that, then we need to, it tells us, add the number of places the decimal moved to the exponent. So we moved 2 places to the left, we're adding 2 to 0. So this is 0 plus 2. Okay, now we'll have a little mnemonic device below to help us remember when do we add and when do we subtract. If the decimal moved to the right, we will subtract. So notice left, we're adding, right, we're subtracting the number of places the decimal moved from the exponent. So for example, that one was needing to move to the left, but what if our original number was 0.03 times 10 to the 0? Because we're saying this was just 0.03, we're throwing on the times 10 to the 0 to start us off in scientific notation, but we need to adjust it. So we need to move to the right this time 2 places to get a singular digit 1 through 9 in front of our decimal point. So this would be 3 times 10, and it's going to be subtracting the 2 places we moved. So this is negative 2. Let me make that a little bit clearer. The negative kind of got clobbed together with that. And that came from doing the 0 we started with and subtracting the number of moves we had. So that can get a little tricky sometimes, thinking, okay, when do I add, when do I subtract? So we have this nice little mnemonic device or memory trick down here. It says LARS. If we move a decimal to the left, we need to add to the exponent the number of places you moved it. So you don't just add a 1, you add how many places did we move it to the left. And if we're going to the right, we're going to subtract the number of places we moved from our exponent. Now, another good way to check yourself on this is there's just a general rule of how you can see how numbers are supposed to look. So this is kind of Miss Metzger's extra little check. If your number in standard form, which was the original way we started with it, so standard form was greater than or equal to 10. So this is case 1. That's 742 I showed you up here. If it's greater than or equal to 10, you should have a scientific notation that has a positive exponent. Okay, notice ours was a positive 2. If the number you started with in standard form, so just a regular number form, was less than 1, then your scientific notation should have a negative exponent. Okay, so numbers greater than or equal to 10, and why we start with greater than or equal to 10 is because remember, a singular digit of 9 in front is the biggest we can go with our scientific notation in proper form. So 2-digit first number is 10. So if we're 10 or bigger, then we go to scientific notation, we should have a positive exponent. Okay, that left add, moving our decimal to the left, which is what we had to do when our number was bigger than 10, we had to move it to the left, gives us that positive exponent. If our number that we started with was less than 1, 0.03 is definitely less than 1, then when we change it, we're moving it to the right to get it to be a single digit, 1 to 9. And we're going to be getting something small, very, very small. So it's going to be a negative exponent. Okay. So we're just going to do some practice with these. Examples of changing numbers from standard form to scientific notation that require moving the original decimal to the left or not at all. This should also say to the right. I combined these as well. So identify 100, looking at this, 140,000 in scientific notation. We want to write it that way. So we're going to be writing also 0.00459 in scientific notation. So one of these numbers is bigger than 10. The other one is less than 1. So just to get us both varieties. So we need to identify the target location for the decimal, move the decimal behind the first non-zero digit from the left, count the number of places in the direction you move the original decimal to the target location. Going from standard form to scientific form, remember moving left will be a positive exponent, moving right will be a negative exponent. So if we look at this one, 140,000, the decimal was originally right here. We're moving that 1, 2, 3, 4, 5 places to the left. Okay, so that means we take our, if you think about this, remember having an original times 10 to the 0, that means we would be doing add 5 to our exponent. So remember, left add. It's always hard to think it in my brain and say it at the same time. So that is why we get 10 to the 5th. For this one, notice to get it to the correct scientific notation, we need to move to the right 1, 2, 3 place values, because that 4 would be a single digit 1 through 9 that would then be right to the left of our decimal point. So 4.59, we moved right 3. So that's going to be, if this was times 10 to the 0, think about our starting point, we're going to be subtracting 3. So left add, right subtract, LARS. Okay. Now, again, another way I could have done that was I could have just counted how many places did I move it and remembered numbers greater than or equal to 10 in their original format, we're going to have a positive exponent, and numbers that are in standard form and less than 1, they're going to have a negative exponent when they're in scientific notation. So a couple different ways you can think of that. So we're going to practice going from standard form to scientific form for the following numbers, and they're all in standard form over here in this left column. So this is 579 million. I need to move that, and I'm going to change colors just so it's a little brighter. Here's my decimal currently. I'm going to be moving this 1, 2, 3, 4, 5, 6, 7, 8 places to the left. So that would be 5.79 times 10 to the positive 8. Okay. Here's my decimal point here. I'm going to move this 1, 2, 3, 4, 5, 6. Got a single digit in front of my new decimal location. It is 1 to 9. So this is 1.327 times 10 to the, and I forgot how many we moved it. 1, 2, 3, 4, 5, 6. So positive 6. Original numbers both greater than or equal to 10. Notice positive exponent. Moving left, add to the exponent. Okay. Also note, I didn't add any zeros as my number in my decimal place after the last significant non-zero number. If I'd had like a 3 here, so say I'd had 579,030,000, I would have added this 0 and that 3. It's once you have just a string of zeros down to the decimal that you can drop those off. So just make sure you get all digits that are not 0 included in your answer. So that would be the only time we would need to add on those zeros when we're in the whole number format, okay? For this one, 537.6 to be in proper scientific notation needs to have the 5 in front of the decimal. So that would be 5.376. Notice all of those are non-zero numbers. I want to make sure I include all of them. And then this is moved to the left 2, so times 10 to the second. These are a little different. This is million, trillion, and billion. So these are words, but we can write those numerically. So 5 million is 5 followed by 6 zeros. And that is from day 1 when we talked about place values. So remember, you would have already seen this before watching this video. So 5 million has, like I said, 5 and then 6 zeros. The decimal's at the end of that. So we need to move this 1, 2, 3, 4, 5, 6. So 5 times 10 to the 6th. And that also on day 1, we learned that million, the word, can be represented by a 10 to the 6th. 3 trillion, that's going to be quite a few zeros. So that's 3, and then it's going to be 1, 2, 3. That'll be the billions, the millions, the thousands, and the ones. So this is 12 zeros. So we also learned on day 1 that that can be shorthanded to 3 times 10 to the 12. Because our decimal point would need to move all 12 places to be right behind the 3. 8.4 billion would be 8,400,000,000. So that is going to be 8.4, and we don't have to adjust that since it already has just one single number in front of our decimal. So in the original setup, so this would be just times 10 to the 9th. Now you can double check that, move your decimal 9 places to the left to get it between the 8 and 4 again, and that is adding 9 to our exponent. Now the rest of these are all numbers that are less than 1. So the first group were all greater than or equal to 10, some of them much greater than 10. And then these are all numbers that are very small, so less than 1. So all of these should have negative exponents when we write them. So notice we're going to be moving to the right on each of these to move it to the correct location. We need this to be between the 6 and the 8 so that we'll have a single digit 1 through 9 in front of our decimal place. So this would be 6.82 times 10. And that's moving 4 places to the right. So remember, we subtract that from our exponent, so -4. This would be moving 1, 2, 3, 4, 5, 6 places to the right. So that's going to be 3.76 times 10 to the -6. 2 places to the right for the next one. So we get 2.6 times 10 to the -2. We need to move the next one 3 places to the right, so we get 3.04. Notice I am including that 0 because it is then followed by a digit that is not 0, times 10 to the -3. And this one is 1, 2, 3, 4, 5. So 9.21 times 10 to the -5. Now, what do we do if we have a value that already is in the correct form? In other words, like 7.25, there's nowhere to move that decimal. Again, we talked about this a little bit when we were talking about the adding or subtracting. In scientific notation form, no movement at all is written as the 10 to the 0, okay? All right, let's look at examples of changing from scientific notation back to standard form. So if the power is positive, we're going to be multiplying by a power of 10 over and over again. So like, think about 10 squared, you're multiplying by 100 or times 10 times 10. So your value is going to become larger. You're going to be moving that decimal to the right. Remember, those numbers that had positive exponents on their scientific notation form, they were numbers greater than or equal to 10. If a power is negative in scientific notation form, you're actually dividing your original number in that scientific notation, the part that's out front, by 10 repeatedly. So it's going to be becoming smaller and smaller and smaller. We're going to be moving the decimal to the left. And that should track back to negative exponents. The standard form should look like it's less than 1. And positive exponents, the standard form should be a number greater than or equal to 10 when you visually look at it in the standard form. So you can check these again in your calculator and think about what is reasonable. Remember, it's not always just adding the number of zeros in front or behind that you're given digits. It also depends on where the digits are located. So like for this very first one, we're not going to just add 6 zeros. That's not moving the decimal to the right. That 6 places, that would be moving it actually more than 6 places. Because to get this started, your decimal's behind the 3. So we have to move 2 places to the right before we could start adding any zeros. So we would have 3, 4, 7. We've moved 2 places to the right. So we need to move 4 more places to the right. And a movement to the right without a digit, we add a 0 in. Okay. So if we check, this was 3.47. So 1, 2, 3, 4, 5, 6. It has been moved 6 places to the right. So in standard form, that is 3,470,000. This one has a negative exponent. So we're going to be getting an answer smaller than 1. So I'm going to go ahead and put a 0 point here. And we need to move it to the left 4 places. So that's 1, 2, 3, 4. So we're going to have 3 zeros, and we also had to move to the left past our 5. So 1, 2, 3, and then our 5, then our 4. So 0.00054. This one again is moving to the left, this time 6 places. So it's going to be smaller than 1. So we're going to be moving 1, and then we need 5 0 placeholders for those moves. So 1, 2, 3, 4, 5. So 5 zeros. And then the rest of our numbers, 6, 0, 2, 3. This is going to be moving to the right because we have a positive exponent. So we have 8.0 currently, and we're going to move. Now this time, because there is nothing after the decimal point, you are going to be adding 7 exact zeros here. That's the only time it is exactly the number of the exponent is how many zeros you add. It's if you have a singular digit only. So that's going to be 8, and then 1, 2, 3, 4, 5, 6, 7. So that is 80 million. And then 2.4 to the times 10 to the negative 1, we'll move 1 place to the left. So that is 0.24. Okay. Now, some questions that might come up in your homework examples. These are specific ones that they're asking for concept checks. 4 times 10 to the 11th would be written in standard form as 4 followed by how many zeros? Well, because it's a 4.0, if we start moving to the right 11 times, we are going to be adding 11 zeros. This one is the first one we'll be adding. So we will be adding 11 zeros. That's different than the next question. It says the GDP in the first quarter, which means gross domestic product, of 2014 was 1.71 times 10 to the 13th. This would be written in standard form as 171. Notice they've already done 2 of those moves for us. So that's 2 moves, plus we would still have 11 more we would need to move. So the 171 is already taking care of 2 of the 13 moves to the right. So we would have 11 zeros we would need to add in. 1.5 times 10 to the 7th would be written in standard form as a 15, followed by how many zeros? Well, this is 1 move out of this, the 7 that we need to move. Plus we need to do 6 more moves. So that's going to be 6 zeros we'll be adding in. Now the next ones, they're just asking us what the correct exponent would be. 0.000089 would be written in scientific notation as 8.9 times 10 to the nth. The value of n would need to be negative or positive. Since this is less than 1, that is going to be a value that is negative. And then we need to talk about how many places we moved for that n value. And so this n is what that exponent value is. So that would be 1, 2, 3, 4, 5, 6. So it is a negative 6. 463 million would be written in scientific notation as 4.63 times 10 to the n. The value of n would need to be negative or positive. This time our number is greater than or equal to 10 originally, so it's going to be positive. And we need to move it 1, 2, 3, 4, 5, 6, 7, 8. So positive 8. Okay, so that ends our discussion on the scientific notation material for the video weekly information. We'll still be doing, like I said, scientific notation in class time as well, especially operations with scientific notation. So we're looking at, this is some information to help us get into the intro of proportions and applications for the 1B2 material. First of all, we want to make sure we know what a proportion is. So it is two equivalent ratios, A over B equal to C over D. It's very important that you recognize that it is a single fraction equal to another singular fraction. No other things plus or minus on either side. Then if that is true, then proportionality comes into play when we cross multiply or cross product. So A times D, that is this diagonal right here, is equal to C times B or B times C. It really doesn't matter which one you multiply first in the listing, as long as you're multiplying the diagonals together. And it is going to be that the diagonal AD multiplication is equal to the diagonal BC, okay, multiplication. So this is sometimes called cross multiplying, like I said, or cross products. If the cross products are not equal, then you do not have a proportion. So we're just going to practice in this specific section, working out some proportions using this cross products. And all of our answers, if they don't come out nicely, we're going to round to the nearest hundredth as needed. So when we're looking at this number 9 here, we're doing 5 times 24. So the first couple of ones of these, I will write out all my steps. After that, I'll start pulling up the calculator and we'll use it. Equals 12 times x. And in fact, I do want to have my calculator ready. So let me grab that. Okay, so you should see my calculator here in the top right. Obviously, you'll be using your handheld one to do these. But we want to do 5 times 24. So 5 times 24. That is 120. Equal to the 12 times x. Now, when you're solving for x, you want to get rid of everything that's connected by an operation to x. So this is connected by multiplication when you don't see anything in between them. So we're going to divide both sides by 12 because 12 divided by 12 is 1. So that would just be 1x. So 120 divided by 12, I don't need my calculator for that one. That is 10. But we can check it if we need to. So for our number 10 down here, we're going to be doing 23 times x. Equals, and I'll go ahead and multiply this one since this isn't too bad. 7 times 11 is 77. So notice x is connected to 23 by multiplication. So I need to divide both sides by 23. So 77 divided by 23. Now notice this comes out to a long decimal that never ends and doesn't repeat. So this is a non-terminating, we call non-repeating decimal. We went around to the nearest hundredth, which is, remember, that's going to be to the second place after the decimal. We have our tenths and then our hundredths. So I'm going to write out about 6 place values and just dot, dot, dot. When I do that anytime in a description, that means I'm telling you that the decimal keeps going. I always write out more than I need and then show my rounding steps. So x equals, need my calculator back up, 3.347826, 347. 826. I didn't write the 3 at the beginning. So let me back that up just a little bit. It is 3 point, and then this just keeps going. So we're trying to round to the nearest hundredth. So I'm going to circle or underline. I like to underline the number that I'm going to. This is my hundredths place. And we are going to look at the digit directly behind it. Remember, we learned about rounding on day 1. If this digit behind it is a 5 or larger, it rounds this up. If it is a 0, 1, 2, 3, or 4, so 4 and below, we do not round this up. So x is approximately, that means we've rounded, it's no longer its original, decimal point that went on forever, 3 point, this would be 3, 5. Because the 7 is going to bump that up to a 5. Okay, let's go to our next one. We have 56 times 4. Don't know that off the top of my head. So 56 times 4 is 224. Equal to 9 times x, which is 9x. Need to divide both sides by 9 to get the x by itself. So we're going to be looking at our calculator and doing 224, which I already had there, divided by 9. And that is 24 point, it's 8 repeating. At the very end, they do a 9 in the calculator. That's because the calculator auto rounds this because it only can hold so much memory of the place values, but this is technically 8 forever. So I'm going to just write out, it's equal to 24.8 repeating. So we're gonna write quite a few 8s. And then just dot, dot, dot. We know it keeps going. And the reason I'm not writing the 8 with the repeating symbol on top of it is because we're rounding the answers to the nearest hundredth. So right there, that's our hundredths place, that second 8. The number behind it is definitely bigger than 5 or equal to 5. So 5 and bigger. So this will be X is approximately 24.89. Okay. Next we have number 12, which does 50X and 12 equal to 12 times 13. That's 156. Divide both sides by 50 since we want to get the X by itself. So 156 divided by 50. Now this actually terminates at 3.12, which is in the hundredths place. There is nothing behind that. We don't round something that's already terminating into the correct place value. Now, if it had been like a 3.123, we would have looked at the hundredths place and the number behind it and determined if it was rounded or not. And then my last one in this little section, we're going to look at, this is 0.27m equal to, we'll need our calculator, 0.3 times 0.14. That is 0.042. So that's my other diagonal. Be careful here. A lot of times I see students divide by this one because they're not paying attention because they say, oh, it's smaller. We don't always divide by the smaller number. We divide by the number that is multiplied by our variable. So we're going to divide both sides by the 0.27. And that is, it looks like 0.15 repeating. So notice second place value, the hundredths place value is the 5. There is a 5 or larger behind it, so it is going to round up to 0.16 to the nearest hundredth. Okay, so that is the cross products, or how do we solve proportions? Let's now use that in some application problems. So we have that Jen can groom 3 dogs in 2 hours. So we're going to be using labeling when we do these types of problems because we're going to have these proportions set up of if she's working at the same speed, how long will it take her to groom 8 dogs? So we're assuming, making an assumption here that she's working at the same speed. She's keeping everything proportionate. So we're going to keep dogs over hours for the given information, and we're going to set that equal to how many dogs over how many hours in the one we're making the prediction on. So we have 3 dogs in 2 hours. And then we know that she's going to work on 8 dogs total for that day. So how many hours will she be working? So this is her rate that she's working at, her speed. This is the whole day. We can consider that. That's her whole day. So how much hours does she need to set aside to finish all 8 dogs' groomings? So we're going to do 3 times x equals 2 times 8, which is 16. And we're going to be doing, move my calculator over, 16 divided by 3. Oops, clear that out. So 16 divided by 3. So it looks like, and we're still using our rules about rounding to the nearest hundredth, it looks like we're going to be doing 5.33 hours of work. So if you want to see that decimal again, it's 5.3 repeating. Hundredths place is a 3. There is a number less than 5, so 4 or smaller behind it, so it does not round up. So to get all 8 dogs groomed, if she's working at the same rate, then it'll take her 5.33 hours. And notice I did put units with my final answer. A lot of times in Newton, you won't be doing that. They'll have it in a text box already out to the side or written after the answer. A lot of times you'll just be entering in your numerical value. So just pay attention to that when you're doing your homework so you don't miss something because you typed like hours in when they already had it as part of the answer. So we have 5 pairs of socks cost $6.99. So $6.99 for 5 pairs. That's a relationship tied together. How much would it cost for 12 pairs? So we don't know the money, and we need to do 12 pairs that we're going to buy. So again, notice this similarity. We're keeping money over pairs and money over pairs. We're keeping this set up the same way so that we can be talking about these comparisons. If it's $6.99 for 5 pairs, how much is it for 12 pairs? Okay. Now, if you wanted to do pairs on tops and money on bottom, you could. You just have to be consistent on both sides, okay? So this is going to be, and this is where you can, you'll start seeing a pattern when we're cross multiplying, and I start doing a little bit less on kind of my paper. I want you still to show your work, but when we get through a lot of these in class, sometimes you'll notice that I won't write every single step down. So please make sure you're doing that for exams, because that's how I grade your partial credit. But I do want to show you that there's a pattern that starts to evolve. So when we're doing cross multiplication or cross products, the part that's across from our variable is always the part we end up dividing by. So it is possible just to type this in on your calculator as do the diagonal that has two numbers in it. So 6.99 times 12. And then you divide that answer by the number that's across from the variable. Now that's only if we have just like singular variables and numbers in each part. Obviously, if you get into algebra, where you might have like x plus 5 or x plus 1, where you have more involved non-singular entries on each part, then you can't really use this trick, but for our class, we can. So we're going to be solving that as 16 point, it'd be 7.7, and the 6 would bump that up to a 7.8. So this is going to be $16.78. So I do want to show you that there are sometimes shortcuts, especially if you're doing a longer problem and you need a way to get through it in the time limit that we have for the class. I would still, if it was me, just to make sure you get all your partial credit points in case you type something wrong in on a calculator, because then I can't see any work. I would at least write this much, you know, show me that you knew that this was the cross products, and then you could use your calculator to just type it in like I did. Okay. And that was money. So notice I put the dollar symbol there. Again, Newton might just have the dollar symbol out front or the word dollar at the end, and you're just typing in your rounded decimal. So at number 16, if 10 pounds of fertilizer cover 350 square feet, notice I didn't set up any proportion formats for us here for our labels. How many pounds are needed for 6,400 square feet? So I'm going to do pounds over feet squared, which you can write as this instead of writing square feet, equals pounds, again, over feet squared. The relationship we were given was that 10 pounds works for 350 square feet. How many pounds, so we don't know the pounds, are needed for 6,400 square feet? Okay, so I'm going to be multiplying. I'll go ahead and write down 10 times 6,400 equals 350 times x. That's my showing my work part. And then on my calculator, I know I'm going to be doing 10 times 6,400. Get that and divide it immediately by the 350. And rounding this to 2 decimal places, we would have, or the nearest hundredth, we would have a 5 in the hundredths place with a 7 behind it. So it's going to be in 0.86. So 182.86, and this is in pounds. That is how much pounds of fertilizer would be needed. Okay. We've got a couple more of these, and then we're going to look at our last section, 1B3. I have a few things I want to do for you in video format there. So we have, if the car travels 254 miles on 8 gallons of gas, so we're going to be doing, it looks like miles over gallons. Find the amount of gas required, so that's going to be the gallons of gas, so we don't know that, for a 900-mile trip. So you can write miles or you can use the abbreviation. But we had 254 miles for 8 gallons is what our car can use. So how many gallons would we need if we need to travel 900 miles? Okay, so I know that's going to be 254x equals 900 times 8. That's my cross products. So 900 times the 8 divided by the 254. Rounded to 2 decimal places again, because all the ones in this section are going to follow that. This would be 0.34, and the 6 bumps it up to a 3.5. So it would be 28.35 gallons of gas. And again, you have to read the directions in Newton for what to round to. I just wanted to keep everything simple for this video, and I'm rounding everything to the nearest hundredth. It may change on a question by question basis in Newton, so make sure you're checking that as you read the problem. The ratio of a length to a width, so that's important, length to width is 8 to 1. So that means length over width is how they're setting these up. So 8 to 1. If the length is 32.4, so that's going to go on top with length, how wide must it be? So there's our setup. So length over width. So this is going to be 8x equals 32.4 since it's times by 1. So 32.4 divided by 8 is 4.05. And that is an exact answer since we're not rounding anything since it's already at the hundredths place. And this is in meters. And again, remember what I said about Newton not always having you enter those units. It's usually as a text after the number box. Okay. So 1B3, proportions, rates, and using proportions to compare. So that's what we want to cover on this weekly video. We're going to set up our templates and make sure we label to make sure we line up our proportions correctly, just like we've been practicing. We're going to use good reading comprehension skills. Make sure we cross multiply and solve for the unknown. Follow any directions on rounding. And remember, we do not round until the very, very end of all the procedures. Notice I never rounded anything off in any of my intermediate or middle steps. It was always at the very end. We will also look at what if questions. This covers finding out what a value would be if it was proportional to another set of data. Even if we actually know the actual value, what would it be if it were proportional to that another scenario? So you may know the exact population of a state, but we might want to say, what if it's proportionate to another state? Okay, so it's like a predicted value based on the proportional relationship. All right, so we're going to review unit rates again. This was something that's covered in our day one material, just to help us kind of get our head wrapped around these proportion problems. So here's an example I've already got worked out that we're going to read through. In 2021, Madison Square Garden employed 8,900 people. For a basketball game at the Garden, there are seats for 19,812 fans. What is the number of fans per employees during a basketball game? Round to the nearest tenth. So fans per employees, okay? We have the number of fans in 2021. We have the number of employees in 2021. We have those actual values that were given to us. We're actually going to be finding the unit rate. Now, in the section when we covered this, we just said divide that by that and you're done. But you can also think of that as proportional. We can say it's X fans per one employee, and we could take off the S for that. It's not really plural. So X fans per employee. So that's really a unit rate. So we had 19,812 number of fans. We had 8,900 people employed. And then we're saying how many fans per one employee. So if we cross multiply on this and solve, so 19,812 times 1, and then we'll end up dividing by that 8,900, you'll see that it gives me this and it keeps going forever. So if we round that to the nearest tenth, that's one place after the decimal, and we look at the digit behind it, it's less than 4 or less, so it's not going to bump that up. So it's about 2.2 fans per a single employee. So if you were trying to figure out, you know, logistics of do we have enough employees to help the number of fans that we're going to have, we'd have about 2.2 fans per each employee. And of course, you can't have partial people, but this is just giving us that unit rate. Okay. Now let's look at an example where we have to set it up. So there are 58 Disney feature films, and there are 285,713 residents of Orlando. I'm sure that number is different today, but as of the time of this question, how many people live in Orlando per feature film? So population in Orlando per one feature film. So we're going to do the total number. We're doing people who live in Orlando on top. So no total number of people living in Orlando. Just going to abbreviate over the total number of feature films. We're going to abbreviate that as well. And we're going to be finding that unit rate of that. So per one feature film. So total, it's just going to be how many people live in Orlando per one feature film. And we're going to round this to the nearest whole number. Okay, so 28,500, or excuse me, 285,000. Yeah, reading and writing is not always easy. 285,713 divided by 58. That's the number of total feature films, total people living in Orlando, equals X out of 1. So I'm going to get my calculator out. So 285,713 times 1, and then divided by the 58. That's going to be X is equal to, I'm going to write this out and then round it, 4926.086, and it keeps going. We're rounding to the nearest whole number. That's the ones place value. So this 0 behind there does not bump that 6 up. So it's going to be approximately 4,926 Orlando residents per feature film. Okay. What is something else we can do with proportions? Well, we can look at, this is kind of an interesting discussion into how we can compare total population to just a smaller subset of the population. For example, you might want to, instead of just saying this is the total number of deaths in a year and the total population of Texas, we might just want to talk about it more on a granular, like city level, and say you have 100,000 people living in a specific city in Texas. What do we maybe anticipate the number of deaths to be? So we're scaling it down, essentially, is kind of what we're talking about here. So I've got this one pre-worked up so that we can talk through it. It says Texas averages 198,106 deaths each year for a population of 29,472,295. How many deaths could we compare to 100,000 people in Texas? Round our answer to the nearest whole number. So notice I've got my total deaths per year in Texas and my total population of Texas. And I'm relating that down to just how many numbers of deaths would that be per 100,000 Texans, okay? So we have 198,106 total deaths in the state. And again, that's an average, but we're using it as our total. And then we're saying total population of 29,472,295. We want to know roughly how many deaths is that for every 100,000 people in Texas. So I've already cross multiplied here and got those large numbers. We're dividing by the 29 million number because it's next to the X. And that comes out to about 672.177, decimal goes on forever. And rounded to the nearest whole number, that 1 does not bump the 2 up, it would keep it a 2. So about 672 deaths per 100,000 Texans. Okay, so let us try one of these together. So I have Indiana averages 82,650 births each year to a population of 6,745,360. How many births could we contribute to 100,000 people in Indiana? Round to the nearest whole again. So we're looking at total births in the year, and that's by people just living in Indiana, over total Indiana population, so I'm abbreviating some of this, equal to how many births in Indiana can we attribute to every 100,000 people living in Indiana? Okay, or Hoosiers, if you want to say Hoosiers. So we are going to plug in our numbers. So because that Hoosiers is what we call people who live in Indiana. 82,650 is the births, total births in Indiana. The total population as of the time of this question was 6,745,360. We want to know how many births is there per each 100,000 people living in Indiana. So I'm going to use my calculator instead of writing out all of these large numbers. Now I might write out my, what did I multiply? 82,650, times 100,000, just to show some partial credit work. 6,745,360 times X, but let's do it all on our calculator so we don't round to the very end. So 82,650 times 100,000, and then divide that by 6,745,360 to get our X by itself. That is 1225.2. We're rounding to nearest whole, so that 2 is not going to bump that 5 up. So X is approximately 1,225 Indiana births per 100,000 people in Indiana. Okay. All right, we just have a couple more things we want to go through. These are, next couple of problems are using proportions to make comparisons. This is the ones that I said you have to be really careful about, because sometimes, not specifically in the ones that I've written here, but sometimes they will give you all 4 numbers that are actual values of those states or those locations. But the way they phrase the question tells you which one of those we're making a prediction about. So I try to be very intentional with the way I did this first example so that you could see why I have actual, but predicted in one specific spot. So it says Iowa has on average 37,785 annual births compared to 30,530 annual deaths. So we're talking about births compared to deaths. So notice births on top, deaths on bottom. If Maine were proportional to Iowa in annual births to death, and we know that Maine averages 14,676 annual deaths, how many annual births should Maine expect? Again, based on this proportionality relationship that Maine is proportional to Iowa. The one that we're proportional to, you will always use both of their actual values. The one that we're relating to it, so Maine is being related to Iowa, you're going to have one of their actual values in your fraction, and the other one is the predicted value. The predicted one, based on that proportionality, is going to be the question they've asked. How many annual births should Maine expect? Okay, so that's kind of how these are set up. And we're going to round this answer to the nearest whole number. So in this problem, we're relating Maine to Iowa. So we will be predicting the expected number of births in Maine based on Iowa's actual numbers and Maine's actual number of deaths. So we have actual Iowa births, actual Iowa deaths equals predicted number of Maine births over actual Maine deaths. So we're saying even if this number on top may not be the actual number of births that happened in Maine, but it's the prediction based on the fact that we're giving you of Maine being proportional to Iowa in this ratio, okay? So Iowa births was 37,785. Iowa deaths for the year was 30,530. We're predicting the number of Maine births based on this proportionality relationship. And we knew that the deaths was 14,676. So I cross-multiplied, got this really large number for 37,785 times 14,676. We got 30,530x on the other side, and I divided both sides by the 30,530 to get the x by itself. So that came out to a non-repeating decimal. It was 18,163.5329, and then it just goes on forever. But we're rounding to the nearest whole. So I just needed to know the digit after the decimal place for that. So 3 is going to get bumped up by the 5 since that's 5 or higher. So this is going to be 18,164. And that is deaths predicted in Maine based on the proportionality to Iowa that we were told about. Okay. So let's try one together. I had to repost the notes. This one originally had a typo, I believe, in it. So I fixed it. It's fixed in this version, but if you happen to print in the first 20 minutes that the notes were up there on this weekend, you might have Delaware right here, which you shouldn't have had. So this is the correct version of that question. So if yours has Delaware down here in the question part, make sure you change that to Alaska. So it says Alaska has 49 Starbucks for a population of 741,204, while Delaware has 25 Starbucks. If Alaska were proportionate to Delaware in their Starbucks to population ratio, how many people would Alaska have? So what's the population of Alaska based on that proportionality? So we are going to be using actual, because Delaware is the one we're relating to. We're going to use actual Starbucks for Delaware. I'm going to abbreviate some of that over actual population in Delaware equals, and again, we are asking for a predicted population for Alaska. So I know I'm going to have predicted Alaskan population. And we're going to use our actual Alaskan Starbucks numbers. Okay. So 49 over 74,1,202, so that's 71,204 equals actual Starbucks in Alaska, which is 25, over the unknown population of Alaska. Again, predicted unknown population of Alaska. We're going to round this to the nearest whole number. So always check your directions for rounding. So this would be 741,204 times the 25, which I'm going to write this one down. It's 18,530,100 equals 49 times X. So we're going to divide that by 49. And that's going to be, I'm going to go ahead and round this to the nearest whole. There's a 0.3, so the 5 will not get bumped up. So X is approximately 378,165. And this would be predicted population of Alaska based on the proportionality to Delaware. You don't have to write all of this, but I feel that it's, when you go back and look at it, it helps you see. You could just say population of Alaska or people in Alaska, but this helps you realize that this is not necessarily the actual population of Alaska. It's what it would be if it had a Starbucks to population ratio exactly the same as the ratio that Delaware has. Okay, so that's what we're doing with those. All right, last thing, I know this was a long first video. Luckily, for weeks 2 and on, there'll be 2 separate sets of videos where I'll still post one big set of notes, but I'll break it up into 2 because you will have one to watch before each class session. So this is using scientific notation in proportions. You'll notice I'm writing my scientific notation a little differently in this specific section. This is going to come up in some word problems in class where we have really large numbers and we're trying to solve these proportions, but they're using words like millions and billions and trillions. And we'll need to maybe write some things in scientific notation just to make our calculations go easier. But another way you'll notice that I've changed this is instead of writing 2.6 times 10 to the 4th for this first one right here, I don't want that to look like a variable. Times, that's an X symbol, can look like a variable. And if I put a dot, sometimes that gets lost, or put it too low, you think you got 2 decimals. So I like to write, when I'm doing these cross multiplication problems with scientific notation, I kind of make my multiplication indicated by a parentheses. So this is 2.6 times 10 to the 4th. Remember, parentheses around something and nothing next, nothing in between that and another number is also another way to write times. I just find this is a lot easier because then the only thing that looks like an X in my problem is the X. Now you can get around that if you call that an N or a P or some other letter, but still we're so conditioned to solve for X in our heads. It's kind of part of our algebraic society that we've learned to always kind of solve for X, that I still think seeing the X in the scientific notation sometimes will confuse people when they're solving it. So this is my personal preference. And this is what I'll do in class, but to help you see that we are still multiplying it as the scientific notation form. It's 2.6 times 10 to the 4th, but the only variable there is definitely sticking out to us so we know what we're solving for. So we're going to practice cross multiplying when some or all the values are written using the powers of 10. You can use the product or quotient rules or a combination of each from the previous sections, or use our calculator to solve the problems below. So we're going to be solving for X and write our answer in standard form rounded to the nearest whole number. So this is 2.6 times 10 to the 4th over 5 equals 7.2 times 10 to the 7th. So notice both of those are in scientific notation over X. If I cross multiply, I'd be doing 2.6 times 10 to the 4th times X, and 5 times 7.2 times 10 to the 7th. You'll notice I'm going to do these a little differently. I could work out these really large numbers, but I'd like to go ahead and solve for X. So I need to divide by this 2.6 times 10 to the 4th to get my X by itself. And notice I didn't do anything on the other side. I didn't multiply anything out yet. And the reason I do this is because I want you to see that we're really just doing kind of what we practiced in our other class session, where we are using operations with scientific notation. You can go ahead and multiply the 5 and the 7.2 together since they're both just regular numbers here. So that would give me actually 36. It comes out nicely. Times 10 to the 7th over 2.6 times 10 to the 4th. And when we do division with scientific notation, we divide the portions that are out front before the powers of 10. So 36 divided by 2.6. And we learned in our first class session that we subtract those exponents. When you have two bases that match and you're dividing, we subtract the exponents. So that's where I got the 10 to the 7 minus 4. This is, again, another reason I don't want you rounding to the very end, because you could round some of this as you go if you were making these big numbers, and you might not get the exact same answer as I do at the very end. So notice if I divide this, I get a non-repeating, non-terminating decimal. And I wrote out a lot of digits just because until you've done this subtraction, you really don't know how many places you're going to be moving that decimal. So this ended up being 10 to the 3rd. So I'm going to be moving to the right 3 places. So I definitely needed more than just a couple digits in my decimal, so I could see what number was behind it and determine if this rounds up or stays a 6. Since this is a 1, which is 4 or smaller, this is going to stay a 6. So this would be 13,846 in standard form, rounded to the nearest whole number. So we want that rounding to happen after we've moved the decimal, okay? Now I did have a issue with this one. Again, if you printed it, it might have a 6 here. I changed it because if we don't change this to a 5, there's actually not enough spaces to see if it rounds or not. So just make sure if your copy has a 6 for this bottom denominator that you change that to a 5 so that this will work out. But this one has 3 different numbers that are all in scientific notation. So we're going to write what our cross products would be first. So this is 4.63 times 10 to the 4th times x, because that's our diagonal, equals, I'm going to have 5.91. I'm going to go ahead and put all the numbers up front together, 6.23, because multiplication, 3 times 4 times 5, you can do 4 times 3 times 5. It should still equal the same. We are multiplying everything in this diagonal together. And then I'm going to put my 10s next to each other, 10 to the 5th and 10 to the 7th. Okay. One of the first things I notice I can do if I wanted to is I could check to see if I can go ahead and multiply this. If it causes you to round at any point, you don't want to do that. So 5.91 times 6.23, as long as you write all of these digits and it's not something that's going on forever and you'd have to truncate it or round it, then you can go ahead and do this step. So I'm going to write that this is 4.63, 10 to the 4th, and times x. This side, I can combine the two just numbers multiplied together and get 36.8193. Notice that is a terminating decimal. And we can actually go ahead and use what we learned about same base when we're multiplying. When it's same base and you are multiplying them together, we add their exponents. We talked about that in our first class session. So that's 10 to the 12th. So you can simplify that a little bit before you do your division step if you would want. Again, not required that you do the multiplication of the two numbers together, but I would at least combine the powers of 10 and get the 10 to the 12th. But we're going to divide both sides by that 4.63 times 10 to the 4th. Over 4.63, 10 to the 4th. Okay, so I'm going to scroll down a little bit so I have room. 36.8193 divided by the 4.63 is, notice that goes on quite a bit, so I'm going to write it out. X equals 7 point, because again, I don't know how many decimal places I'm going to be moving. 95233. And then we have 261. 339, and I'm going to stop there. Hopefully that'll be enough, and then I'll put my dot, dot, dot. It keeps going. And then this is subtraction again, because it's, remember, dividing same bases. So 12 minus 4, so 10 to the 12th over 10 to the 4th equals 10 to the 12 minus 4, which is 10 to the 8th. So that's why I said you have to be really careful about these. And my calculator actually holds more digits than a lot of the handheld ones. A lot of those stop at the, I think it's the 613. I think they stop there. A lot of them do. And that if we hadn't changed that original number to a 6, we would have actually gone all the way to the edge of that and you wouldn't have known how to round it. So that's why I made that edit before we got started. So this one is times 10 to the 8th. So we need to move our decimal 8 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8. So between that 1 and the 3, and the 3, if we're rounding to the nearest whole, will not bump that 1 up. So that's 7, 9, 5, 2, 3, 3, 2, 6, 1. I'll rewrite that. It got a little squished. And then I usually go back in and put my commas. Usually you don't need to enter them into Newton. It likes not sometimes seeing the commas. Just depends on the computer system. But for most people to read this number correctly in their heads, we need to put the commas in. So remember, from your decimal point, every group of 3, you put a comma. So 795,233,261. So that you could directly enter into your calculator. I do want to show you can do that as well, just because sometimes people, but you would want to still write some of this down, at least the first line or two, so you can get that partial credit in case you make a mistake. But I would do, you always do the diagonal that has both numbers first if you're doing this all in your calculator. So 6.23 times 10, you have to use the exponent button to the 7th. That's this x to the y. Some people have a little caret for that. And then we would times that by, I sometimes put the next part in parentheses, 5.91 times 10 to the 5th, close that parentheses, hit enter. So now it's done both of those. Divided by, now this is the very important part. When you're dividing by scientific notation, and there's like a multiplication between the two parts, you absolutely need to put the whole division into a parentheses, because otherwise it will only divide by the first thing you write, and then it multiplies by 10 to the 4th, which is not what we want. We want it to actually divide by 10 to the 4th. So put that parentheses, 4.63 times 10 to the 4th. Close that parentheses. It's dividing by 46,300. And notice I get that same answer, but it's already been moved for me. And I would see that that now rounds up or stays the same. It rounds as a 6-1. Okay. All right. So that's the end of our first weekly video. Sorry, this one is very, very long. You need to have all of these notes written on either your own paper or a printed copy of this. Remember to turn in for your instructor choice points. Next week, it'll be split up into a video for day 1 and a video for day 2, but still one notes file, so you don't have to print multiple files. There are going to be, though, from this day on forward, it'll be 2 separate videos to watch each week before each individual class session. And it'll always be things that are kind of precursors to what we need in the lesson, or an easier part of the homework that we need to go through before our class time. All right, I hope that helps. I hope you have a wonderful day.